Welcome to the Deep Dive. Today, we are strapping in for what might be the most fundamental shift in computing since, I don't know, since we left the desktop for the cloud.
It might even be bigger than that.
I think so, because this isn't just about faster chips or, better algorithms. This is about changing the core relationship between the human and the machine. We are talking about the agentic revolution. This is the monumental transition from software that follows rigid, hard-coded instructions to systems that are goal-oriented and truly autonomous.
It truly is a seismic event, and it's necessary, really, because the complexity of our modern distributed systems has finally, I think, outpaced our human ability to manage them.
Completely.
For decades, we told computers exactly how to do a task. That's imperative programming, right?
Yeah.
We designed every loop, every function, every little exception handler.
Every single step.
Every step. And now we are entering the era of declarative intent, where we simply state what outcome we need. And the system, through a decentralized workforce of autonomous AI agents, figures out the complex multi-step plan to get there.
So our sources for this deep dive trace the entire history of this change. We're going to detail the walls we hit in every prior computing era, and trust me, there were many. We're also going to look not just at the opportunity, but at the threat landscape this acceleration creates. We'll be examining high-speed AI defense tools like RuVector that are basically necessary to fight AI-accelerated attacks in milliseconds.
And crucially, we'll outline the radical new skill set that's going to be required for every infrastructure engineer, every developer, every security professional by, 2026?
That soon?
Oh, yeah. This isn't a slow migration. It's a necessary transformation. If your job involves a keyboard and code, you need to understand this shift from being a code writer to an orchestrator.
Right, because the complexity you used to manage by hand is now being outsourced to an autonomous AI workforce.
That's the core idea.
Okay, let's unpack this. Our mission is to take you from the historical context of previous failure right to the cutting edge of AI ops, security, and infrastructure. Let's start with a bit of a history lesson.
Good place to start.
This whole revolution is only happening because every previous model of software development eventually and inevitably hit an insurmountable wall.
That is absolutely the central theme. It's this necessity of change, and it's driven by accumulated complexity. In each case, engineers solve the current problem, say moving from machine code to reusable modules.
Right.
But in doing so, they unknowingly introduced a new bottleneck. It was always related to scalability or adaptability or, and this is the critical one, human cognitive load.
So let's start way, way back at the beginning, the golden age of mainframes and punch cards.
The deterministic era.
Exactly. The 1950s to the 70s, this was all defined by meticulously crafted, low-level, hard-coded logic. Think assembly language, COBOL.
Right. It was all about telling a system like the IBM 701 exactly what memory address to hit, when to move data, when to execute an instruction.
So the programs were basically a mirror image of the physical architecture of the machine itself.
They were. And they were incredibly efficient for static, well-defined problems. But the system had almost zero flexibility. The wall they hit was a complete failure of scalability and adaptability.
Because the software was so tightly coupled to the hardware.
And to the initial requirements. You couldn't change it without basically dismantling the entire structure.
And we have a chillingly specific example of just how brutal that was. It wasn't just a technical bottleneck, was it? It was a human effort bottleneck.
Right, a huge one. If a major company needed to update a single payroll calculation, let's say for new tax regulations, on a mainframe system, that could require thousands of man-hours.
Thousands for one change.
Thousands. You had to trace every affected instruction path, manually rewrite the low-level code, test the entire system end-to-end, and then physically repunch the cards.
The idea that a minor regulation change could take 3 months and 20 engineers, it's just unimaginable today.
The manual effort was exorbitant and so error-prone. And this required such exhaustive upfront planning that any kind of iterative development was just impossible.
And the human cognitive load.
It was immense. Even for a minor change, you had to keep the entire low-level machine state in your head. They just couldn't adapt quickly to evolving business needs, which of course is why the next era, the one focused on abstraction, had to arrive.
Okay, so that brings us to the modular era. This is the 80s and 90s, championed by object-oriented programming, OOP languages like C++ and Java.
Right.
And the idea here was brilliant, right? Encapsulate data and behavior into reusable modules, these objects, aiming for manageability and easier composition. We thought we had finally tamed complexity.
It was a monumental step forward, no question. We're moving away from pure procedural logic and trying to make software a set of, standardized reusable parts.
And it let programs get much larger than before.
Far larger. But as these systems grew, especially in big enterprises by the mid-90s, that modularity itself became the source of the next problem. The wall we hit was just pure cognitive overload.
I remember the pain of that overload. So explain why OOP scaled the problem vertically, but not really horizontally.
Okay, so think about it this way. A large project involves hundreds, maybe thousands of interconnected classes and libraries, often written by different teams over a decade. So developers struggle desperately just to manage the complex dependencies and interactions between all those objects. You have these deep, fragile inheritance hierarchies.
Where if you change something at the top.
You risked breaking dozens of derived classes below. It was a house of cards.
And of course, the classic Windows example, DLLL.
Exactly, DLL hell, where some library version in conflict would just break a seemingly unrelated application. It was the perfect illustration that while the individual components were reusable, understanding the entire system's state and behavior became so labor-intensive.
So you weren't even writing code anymore. You were just trying to map the complexity in your head.
All your time was spent just trying to model the object relationships and dependencies. It was exhausting.
So we moved the complexity from managing the machine's low-level processes to managing the application's architectural relationships. But the human brain was still the ultimate bottleneck.
We were still the ones stitching the massive quilt together.
And that leads us right into the explosion of the internet, SaaS, and cloud computing, the connectivity era.
The 2000s and 2010s. This brought us distributed systems, microservices, REST APIs, horizontal scaling, unprecedented flexibility and scalability. We really thought we had solved the scaling problem forever by breaking the monolith into these tiny, independently deployable pieces.
But we just exchanged one monolithic problem for hundreds of tiny distributed ones.
Precisely. The wall here was distributed system complexity. Yes, microservices allowed for independent deployment, different tech stacks, but the operational challenge was immense.
You had to manage network latency,
ensure data consistency across multiple databases, handle authentication, orchestrate hundreds of services that were constantly talking over unreliable networks. It was chaos.
Our sources call this the distributed monolith problem, where all these independent services somehow manage to recreate the tightly coupled, hard-to-change complexity of one giant application.
But with the added horror of network failure.
Exactly.
And that operational overhead, it was quantifiable. Studies from the 2010s showed that many enterprises moving to microservices saw their operational complexities increase by as much as 30% compared to their old monoliths.
So developers weren't just writing features. They were now writing load balancers, service discovery, circuit breakers.
Complex monitoring systems. The cognitive load didn't disappear. It just shifted entirely to managing the deployment, the health, and the whole communication ecosystem.
That's a critical insight. The core value of microservices, which was decoupling, was often canceled out by the sheer amount of integration code and operational tooling needed just to keep them talking.
The human was still in the loop, just managing a different kind of chaos.
Which brings us right up to the doorstep of the present, the co-pilot era, early generative AI.
This was the first time we truly had AI assisting humans, generating drafts of code or text. The first time the computer actually helped with the imperative writing process, suggesting the next function or completing a module.
And initially, this felt like the solution, didn't it? Instant productivity gains.
Oh, it was a phenomenal productivity booster, no question about it. The AI could write boilerplate code, suggest functions, translate simple requirements. It took away some of the manual grind of writing syntax. But it wasn't solving the core problem of systemic complexity or autonomy. It was still fundamentally operating within that old imperative mindset.
Because the wall here was still heavy human oversight. The AI generated the output, but the human developer was still required for heavy validation, for course correction, and for making sure the code actually integrated correctly into the complex system they were managing.
It was augmentation, a powerful digital intern, you could say. But it wasn't a strategic automation engine capable of setting and achieving high-level goals on its own.
We needed a system that didn't just write how to do the tasks,
but could define the task itself, generate the code, deploy it, monitor it, and iterate on its own. That necessity, driven by hitting 4 straight walls of complexity and cognitive overload, is what birthed the agentic revolution.
Okay, so let's unpack this new era, what it is, and why it's so fundamentally different from everything that came before. This is where we stop following instructions and start defining aspirations.
That's a great way to put it.
If the last four eras were about refining how we write code or structure systems, the agentic revolution is about bypassing those manual tactical steps entirely.
And the core definition here is really crucial. Agentic development means goal-oriented autonomous systems. We're executing a sort of philosophical shift from imperative programming.
Which is telling the computer how to do it.
Exactly. To declarative intent, simply telling the computer what result is needed.
Let's use a tangible example to clarify that for the listener. If I were an engineer trying to set up a new logging pipeline in the old imperative era, what would I do versus the agentic era?
Okay, so in the imperative era, era 3, for instance, you'd have to write Terraform to provision the cloud resources, write Python scripts to configure log forwarders, write YAML to deploy a Fluent microservice on Kubernetes.
And that's before you even get to monitoring.
Right. Then you configure Prometheus alerts, write specific filtering logic. It's a multi-day, multi-tool, multi-step tactical process.
Okay, so now in the agentic era.
You simply state the declarative intent. I need a scalable, cost-optimized logging pipeline deployed to our Azure environment that filters out all debug-level messages and alerts the platform engineer if latency exceeds 500 meters for more than 5 minutes.
Okay, that's it.
That's it. The autonomous agent, using its LLM brain, breaks that goal down into the exact sequence of technical steps, executes the code generation, deploys the infrastructure, and sets the monitoring rules without a human touching any of the tactical details.
So the developer's role is fundamentally changing from code writer to orchestrator of this new AI workforce. This is how we move away from that cognitive load bottleneck.
Exactly. And our sources highlight a really significant trend reflecting this. Something like 60% of enterprises are actively reskilling their development teams toward these high-level orchestrator functions by 2026.
60%! That's not a gradual change, that's a frantic necessity.
It is. It's driven by the realization that humans just can't keep up with the complexity they've created.
So the new focus is on designing those complex high-level prompts, configuring how the agents interact with each other, because you might need a coding agent, a security agent, a deployment agent, all collaborating.
A multi-agent system.
And then just validating the final system goals.
It's a systems design at a macro level. The human is responsible for the guardrails and the intent, not the execution. This offloads all that repetitive low-level stuff that caused the cognitive pileup in the past. It's about strategic thinking over tactical coding.
The technical elegance is clear, but the executive suite focuses on the bottom line. So what's the economic justification for this rapid, enterprise-wide transformation? Why spend billions shifting infrastructure now?
The ROI is massive, and it's accelerating. It's driven by efficiency and hyper-personalization. The agentic AI market is projected to reach over $2.1 billion by 2026.
Wow.
That is a 250% plus increase from its estimated size of just $600 million in 2024. This isn't speculative growth. It's driven by concrete, measurable gains.
And crucially, these aren't just future projections. Early pilot programs are showing tangible results right now.
Absolutely. Pilot programs at several Fortune 500 companies have already demonstrated a dramatic 20–30% reduction in overall development costs.
Where does that savings come from?
Automated testing, self-healing systems, agents that perform maintenance tasks while human engineers are asleep, things like that.
That's impressive, but a percentage can be abstract. Do we have a specific dollar value example?
We do. A major telecom company saved an estimated $5 million in a single quarter Q4 2023 just by deploying agents that automatically generated unit tests and performed regression testing.
So that entire labor effort, previously done by highly paid QA engineers and developers,
Just automated away.
that shifts the narrative entirely. The move is no longer about nice-to-have augmentation. It's a strategic automation imperative. If you aren't doing that, you're hemorrhaging millions compared to your competitor who is.
Exactly. The risk calculation changes completely. And developers, the people who have to actually implement this, they seem to be fully on board.
They see it coming.
They do. A global survey showed that 75% of developers anticipate agentic systems will be the primary method for enterprise automation by 2030. They don't see this as job elimination, but as the inevitable path forward.
So all of this goal-oriented autonomy hinges on the AI having the brain power, right? The reasoning capacity to actually break down those complex directives into working code. Is the underlying tech ready?
It is, and it's improving so rapidly. The continuous performance improvements in large language models are the core engine driving all of this. These models are the brain of the revolution.
And we're seeing real progress there.
Oh, yeah. Over the past year alone, specific advancements in model fine-tuning and tool use have driven a 15% increase in agentic problem-solving success rates.
Why that 15% jump specifically? Is it just more training data?
It's more about logical deduction and multi-step reasoning. Earlier models, they struggled to maintain context across more than 3 or 4 sequential steps.
Right.
Newer models, with huge context windows, up to 200,000 tokens in some cases, mean the agents can handle far more ambiguous and nuanced problems. They can read vast configuration files, maintain the state of a complex system, and generate a multi-part plan without needing a human to constantly course correct.
They can act autonomously for longer.
Much longer.
So, agents are faster, cheaper, and smarter. They remove human cognitive load and accelerate development. But here's the critical pivot. If we empower software to move this fast and make autonomous decisions, we are also introducing a new threat landscape that operates at machine speed.
And that forces a completely different kind of defense.
Right.
That's the crux of the defensive challenge. If the speed of development and operation is increasing by factors of 10, the speed of attack is accelerating even faster, which is why traditional human-paced, signature-based security tools are they're falling behind. They're operating with Era 1 logic against Era 5 threats.
So let's detail the threats that make standard firewalls and antivirus basically useless. What are AI-driven attacks doing that requires a whole new paradigm?
Well, the core issue is AI model obfuscation and polymorphic threats. Attackers use sophisticated techniques like adversarial examples, which are these tiny, imperceptible changes to input data or model poisoning to intentionally hide malicious AI behaviors.
And the attacker's AI can generate thousands of new code variants per minute.
Per minute, which means traditional, signature-based tools, the ones that look for a known bad sequence of bytes, are instantly obsolete. The signature is gone before we can even log it.
So we can't look for known malware signatures anymore. We need tools that can spot the shape of bad behavior, the underlying intent, even if the code is brand new.
And that's where RuVector comes in.
Right?
We introduce RuVector as the core technology for addressing this speed and complexity gap. It operates via advanced vector similarity searches on high-dimensional vector embeddings. It's the difference between comparing fingerprints and comparing a behavioral portrait.
Okay, we need to slow down and explain that concept. For a listener who might be familiar with SQL but not vector databases, how does that work in practice?
Okay, so think of every piece of activity, a system call, a user login, a network flow, as being mapped to a complex multidimensional point in space. This is the vector embedding. It's a mathematical representation of that behavior.
So a normal login pattern lands at coordinates XYZ.
Exactly. And a known malicious attack pattern lands at coordinates ABC. So instead of comparing text strings, RuVector compares the distance between these points in mathematical space.
Okay.
So RuVector then performs these nuanced similarity searches. If the vector of a new, unseen action lands mathematically close to the vector of a known malicious behavior, even if the actual code is slightly different, the agent flags it. It identifies subtle deviations from normal behavior because the structure of the threat is the same in vector space.
Even if its surface appearance changes.
That's the key.
This sounds incredibly powerful, but for it to be useful against sub-second AI attacks, the entire security pipeline must operate in near real time. If the data is even a second old, it's too late.
This is the massive challenge for legacy systems. Our sources highlight just how severe this data latency problem is. IBM reported that organizations failed to process a staggering 45% of their security log data.
45%. If nearly half your security logs aren't processed, you're operating with a massive blind spot, and that's against yesterday's threat, let alone today's AI threat.
That's the critical infrastructure gap that Rev.io stream processing modules are designed to solve. The ingestion pipeline itself has to be engineered for extreme performance to feed RuVector.
You can't be writing to disk and then querying.
No, that latency cycle is fatal in the agentic age.
And we have specific, non-negotiable metrics for this performance.
We do. To beat the AI threat accelerator, the injection pipeline must be able to process 1 million security events per second.
1 million per second.
From all sources, logs, network flows, API calls, with an end-to-end latency of less than 20 milliseconds before that data is even vectorized by RuVector.
That is an insane speed requirement, 20 milliseconds end-to-end.
Yeah.
That means you're bypassing traditional databases entirely, right? This is all in-memory stream processing.
It has to be. It's an engineering feat, but speed is the new signature. If your data is 50 milliseconds old, the attacker's AI has already completed its mission. That low latency is paramount.
So once the data is vectorized by RuVector, how do the security agents use this information to fight back proactively instead of just waiting for an attack?
The agents have to prioritize proactive behavioral analysis. By continuously generating and analyzing vector embeddings of normal system behavior, they identify anomalous patterns that indicate novel, previously unseen exploits.
So you're looking for the behavior of a zero-day exploit, not the vulnerability itself.
That's the only effective defense. But the attacking AI knows we're using AI security tools, so they will use adversarial techniques to try and fool the defense.
Which leads to the need for adversarial robustness.
Exactly. The revector embeddings themselves have to be resilient against subtle perturbations. A perturbation is a minuscule change to the input data designed to slightly alter the vector, making the malicious activity look normal to the AI.
And if the defense isn't robust, what's the consequence?
Well, research from MIT CSAIL in 2023 noted that these subtle perturbations can reduce a deep learning model's accuracy by over 30%. The defense has to be trained not just to detect the threat, but to detect the deception used to hide the threat.
It's a perpetual, escalating AI arms race.
It is.
And since we established that human intervention is far too slow, the response has to be just as autonomous as the detection.
Absolutely. It must be autonomous enforcement. Once a RuVector-powered agent detects a critical threat with high confidence, it has to initiate containment like killing a process or isolating a machine within 100 milliseconds.
100 milliseconds.
And we're seeing this in the wild. Studies from Palo Alto Networks this year show that autonomous agents have a 65% faster response time to novel threats compared to traditional SIEMs that rely on human-defined playbooks.
So the power here isn't just in their autonomy, but in their ability to learn collectively across an entire network.
That requires immediate, enterprise-wide knowledge sharing, a real-time threat intelligence sharing protocol. Agents have to instantly share malicious vector embeddings across the whole network using rev.io messaging.
So if one agent sees a threat,
all agents know within milliseconds. CISA reported this can reduce the overall impact of a widespread attack by up to 40%.
And that collective learning loop has to be continuous to adapt.
Exactly. It requires continuous feedback loops that incorporate the results of agent actions. Did the containment work? Was it accurate? To constantly refine RuVector's detection models.
So the defense is always getting better.
It's improving by about 15% over 6 months, according to Google AI, even if the human team is focused elsewhere.
Now let's talk about the integrity of the agents themselves. If the AI is autonomous and distributed everywhere, how do we know the agent hasn't been corrupted?
That's a major concern, especially with supply chain attacks. It's addressed by agent integrity. The system has to use secure remote attestation using cryptographic components. It's like a constant digital checkup.
How constant?
The agent's hardware and software integrity are verified every 60 seconds. IBM X-Force reported a 15% increase in these supply chain attacks, so this constant verification is absolutely necessary.
And finally, for this to scale across the whole enterprise, including resource-constrained environments, the agents can't be heavy.
No, optimization is paramount. The resource requirement is extremely specific, especially for the edge. An edge agent has to consume no more than 100 motor beads of RAM and 5% CPU on a standard IoT device.
In a tiny package size.
Total package size under 20 motor bead. This low overhead is crucial so that security doesn't crush the performance of the device it's protecting.
So we've shifted from writing code to defining goals, and we've established the need for these autonomous, lightning-fast digital immune systems. This clearly means the human roles and systems engineering have to change entirely. The skills that govern the last 20 years are, well, they're rapidly becoming obsolete.
This is probably the most immediate impact for our audience. The automation we just discussed isn't a niche application. It's a wholesale transformation. Agentic engineering is expected to automate up to 80% of certain IT operations.
80%. Things like patching, monitoring, basic remediation.
All of it. And this forces a radical shift for professionals like Linux sysadmins and systems engineers. Their value moves from reaction to design.
Okay, so let's detail the new roles emerging from this. Where do traditional sysadmins go?
They transition into specialized roles focused on enabling and managing the AI workforce. First, you have the platform engineer.
The foundational role.
Exactly. They build and maintain the infrastructure the agents rely on. The secure Kubernetes clusters, the high-speed networking, the data pipelines. They enable others to deploy agents securely.
Okay, what's next?
The AI ops engineer. This is the specialist who truly understands the autonomous system lifecycle. They deploy, manage, and supervise the operational agents themselves, making sure they're running reliably and achieving their goals.
And we also see a specialization emerging at the intersection of data and operations.
Yes, the MLOps platform engineer. This role is expected to see 180% growth by 2026.
180%, that's staggering. Why that specific role?
Because mature MLOps practices are what double AI product time to market. The MLOps engineer bridges the chasm between the data science team building the models and the platform team running the infrastructure. They manage the entire production lifecycle of the AI.
And finally, a dedicated security role.
The AI security engineer. They focus specifically on mitigating vulnerabilities like prompt injection and governing the concept of excessive agency.
The traditional Linux sysadmin needs to become fluent in a new toolchain that's all about orchestration and cloud-native complexity. What are the mandatory technical skills for 2026?
Okay, we can break it down into 4 critical areas, and these aren't optional. They're the new baseline.
First up, cloud-native orchestration. The world isn't on a single cloud anymore. Agents have to operate seamlessly across Azure, GCP, AWS.
Exactly. This requires a universal control plane mindset. 80% of enterprise Linux deployments are projected to integrate multi-cloud management platforms like Google Anthos or Crossplane.
So you define the intent once, and the platform manages the multi-cloud execution.
Right. And since agents are highly distributed and constantly communicating, that communication has to be standardized. That's where service meshes come in.
Istio and Linkered.
Yeah. 70% of cloud-native agentic deployments will use them. The service mesh provides that crucial layer of observability, security, and traffic management between the agents.
Okay, second area, observability. When an agent acts in 100 milliseconds, how do we monitor its decisions? We need kernel-level visibility, which brings us to eBPF.
Mastering eBPF, the extended Berkeley packet filter, is mandatory. Traditional monitoring tools have massive overhead. eBPF adoption is poised for 60% growth for this exact use case.
Why is it so necessary for an agentic world?
Because it lets you safely run custom programs inside the Linux kernel without changing kernel code. This gives you unparalleled, low-level visibility into system calls, network sockets, process execution, exactly where an autonomous agent operates.
So you can spot performance bottlenecks and security anomalies that are too subtle for traditional logging.
And you can do it with zero overhead, which is key.
All right, third area, deployment and management. We have thousands of agents across dozens of clouds. How do we reliably deploy and manage all those configurations?
This is where discipline meets automation. GitOps. GitOps principles are projected to govern 85% of infrastructure and AI agent configurations by 2026. Git becomes the single, immutable source of truth.
And this is enforced by automated tools, not manual scripts.
Yes. Tools like FluxCD and ArgoCD, they're projected to hold an 80% combined market share for GitOps in these ecosystems. They constantly monitor production, compare it to Git, and automatically fix any drift.
There's also a move towards standardization at the OS level.
Right. The Linux Foundation's project, SLICE, it aims to standardize 100% of new autonomous agent Linux deployments by 2026. Robust, hardened, predictable base configuration.
And finally, the fourth area is a new meta skill, prompt engineering. But this isn't like talking to a chatbot for marketing copy.
No, this is prompt engineering for operations. It's crafting the precise, highly contextualized directives for the LLMs inside the agents. It requires a deep understanding of the system state, the tool chain, and the business outcomes.
What's the difference between a bad prompt and a good one here?
A bad prompt says, fix the slow server. It's ambiguous. A good prompt is declarative and detailed. Rebalance the load by 15% across the GKE cluster using the Istio mesh. Ensure P95 latency stays below 100 milliseconds, and log all changes in Git.
And that precision matters.
It improves automation accuracy by 20%. It's the difference between successful autonomy and expensive chaos.
So this shift is massive. New tools, new roles, a whole new way of thinking. But anytime a technology gives software this much power, enterprises push back with legitimate questions about risk.
Absolutely. The revolution won't be adopted if it can't clear 3 massive hurdles that every enterprise buyer brings up: trust, governance, and cost.
Okay, let's take them on. Objection number 1, trust. These systems are a black box. An AI agent acts, but I don't see its reasoning. How can I trust an agent with my core financial infrastructure?
The rebuttal is explainable AI, or XAI. We solve the black box problem by implementing mandatory, transparent reasoning layers. XAI tools achieve an impressive 88% user comprehension rate for agentic decision pathways.
So they don't just tell you what the agent did.
They provide a full audit trail detailing the LLM's thought process, the specific data points it used, and the tools it invoked.
And this often relies on a process called retrieval augmented generation, or RU. Why is that essential for XAI?
RE is vital. An LLM on its own relies on its general training data. RI means the LLM is first grounded in your specific, verified internal knowledge base, your configuration guides, your security policies, your real-time error logs.
Ah, so when an agent quarantines a server, the XAI system shows the ARGI context. It shows the specific error logs and security policies that influence the action.
Exactly. A human can then validate the logic against known truth. It moves the system from a black box to a transparent decision engine.
Okay, objection number 2, governance. If an autonomous agent makes an error, who's liable? How do we ensure compliance with regulations like GDPR or IPA?
The answer lies in robust governance frameworks and ethical guardrails. The key is achieving compliance traceability. Frameworks using immutable audit trails achieve 95% compliance traceability for regulated deployments.
So you can instantly prove why an agent accessed a particular piece of customer data.
Precisely. It turns the automation into a compliance asset, not a liability. And on the ethical side, that's where design guardrails come in. Ethical AI guidelines have seen an 80% adoption rate in regulated industries already.
And things like Anthropic's constitutional AI principles
Are influencing design in 70% of enterprise AI agent deployments by 2026. This bakes the rules right into the AI's training and execution loop.
But we're still aiming for autonomy. So we have to acknowledge that human oversight is the ultimate guardrail. We can't have agents making critical, irreversible decisions without a sign-off.
Right, the human in the loop is still a necessity.
So what does that threshold look like for a system like the RuVector-powered security agent? We need speed, but also caution.
The policy needs to be surgically precise. Our sources suggest a clear rule. Any RuVector-identified anomaly with a confidence score below 85%. So the AI is highly certain, but not absolute. Or any critical action requiring irreversible changes.
Must be escalated for human review.
Within 5 minutes.
Why 5 minutes? That's still incredibly fast.
Because that's the maximum time window for containment in a modern distributed attack. The system handles the low-certainty actions autonomously, reserving human brainpower for the truly complex, high-stakes decisions. It integrates AI speed with human judgment safely.
Okay, final objection. Cost of inference. Running massive LLMs in the cloud to power thousands of agents, all generating tokens, that's financially daunting. How do we make this sustainable?
The solution is local first and edge AI computing. We move the processing away from those expensive hyperscale cloud APIs. We optimize smaller LLMs to run directly on edge devices.
And this solves the latency problem we saw in the connectivity era, where every API call was a network round trip.
Exactly. On-device LLM inference can achieve up to a 90% reduction in latency for real-time applications. If the agent's brain is local, its decision is instantaneous.
And the market is responding to this.
Rapidly. 70% of organizations are prioritizing local-first AI implementations by 2025 for data privacy, reduced latency, and of course, reduced inference costs.
This has been a monumental exploration, tracing the entire arc of software development history right into this autonomous future. We've really seen the critical, decades-long progression of complexity that made the agentic revolution inevitable.
We've established that the move to agentic systems isn't just an incremental step. It's a profound, necessary shift driven by the failings of 4 previous eras: deterministic rigidity, modular complexity, connectivity chaos, and copilot dependency.
Each step introduced a new wall of complexity that the human mind just could no longer scale. The future is characterized by rapid, goal-oriented, autonomous action, powered by high-speed defense like RuVector, and governed by standardized practices like GitOps and eBPF visibility. The operational landscape is, well, it's fundamentally unrecognizable from just a few years ago.
The developer is an architect of intent, not an assembler of code. And we've quantified the reward. These systems are driving 15–20% reductions in operational costs and offering a staggering 65% faster incident response time.
So here's the final provocative thought for you to consider. If the autonomous agent is demonstrably faster, cheaper, and more robust at handling systemic complexity than manual, human-managed processes, the real risk is no longer in deploying autonomous systems.
The risk is in clinging to the human cognitive load and the slow pace of the past.
Exactly. If your infrastructure team can reduce costs by 20% and respond to threats 65% faster, the question becomes, how quickly can your organization make the shift from writing code to simply defining outcomes? That pace of transformation is what will define whether you lead or follow in the new agentic age.